Hey everybody, welcome back. I, as always, am your dog Chili, and this is episode 14 of the HUGS series. And there's going to be a little announcement at the end of this video, talking about a stream I want to make, just basically me fucking around programming with some interesting bullshit. And so if you get bored somewhere throughout this video of my SSE bullshit, you can skip to the end if you still want to hear about the live stream. But anyways, let's get started. Now today we're going to be doing the SSE accelerated version of the Bloom code. It's been a long time since the last video. I know. Shit's happened, life's happened, and other interesting programming projects have caught my attention. And honestly, a lot of it has just been because I've been avoiding debugging this SSE code. It's such a pain in the motherfucking ass. It's one of the great reasons not to do SSE is it's a pain in the ass is what it is. Also a testament to, the dangers of drunk coding or half-assed coding while watching YouTube videos, etc., etc. Measure twice, cut once, and all that happy crappy. I'd like to give a shout out to my man Albino Papa from the forums. He helped me out a little bit in this debugging, got me some motivation to slug on with this, so Papa bless, that's all I gotta say. Now, before I get right into it, just want to make a little disclaimer here. You need to watch my SSE series if you want to be able to follow along with this. I made a series that introduces SSE concepts, so I'm not going to be introducing them here. I'm just going to be talking about their application to this particular problem. So you watch my SSE series. There's 4 episodes of them so far, and so you got to watch episodes 1 to 4 at least. And also, you got to watch the episode that came before this. It talks about the algorithm of calculating the Bloom effect, just the standard algorithm with standard C code. And you need to understand that because I'm not going to explain that shit all over again here. That would just bore the hell out of the people who were paying attention. So watch that and watch the SSE stuff. The lesson is going to move quickly, and I'm not going to go into super heavy detail and everything because this is a very advanced topic. I'm assuming that the people watching this and who are actually following along are at a sufficient level that I don't have to spoon feed every little bit of bullshit. That being said, I want you to watch it. Try looking at the code yourself or fooling around, and if you still don't get it and if you're determined to get this shit, come on over to the forums, ask any questions. We'll be happy to help you. I love answering questions about advanced bullshit. I'm used to answering questions about, the beginner series stuff. So it's nice to get something from the advanced area every now and then. And you know what? If you just don't get this stuff and you just way over your head, don't worry about it because this is not super important. I love this topic. I love this advanced this hardware close to the metal stuff, optimization, but it's not the main skill in becoming a programmer or becoming a game programmer. The number one skill to master is how to fit all the pieces together in a system to make something that works and doesn't become some intractable ball of string that is completely broken and completely unfixable, or that works, but the moment you try to add something to it, it just all falls apart. If you can create a system that is not that, a system that is nice and modular and modifiable, easily debugged, then you have mastered the most important skill of programming. This is just some fun bullshit that I like to do. It's an interesting skill. It's a skill that not many people have, not many programmers have, but it is not the most important thing by far. It's just something that I find interesting and other people find interesting too, and that's why I'm going to talk about it. There we go. That is all of the preamble out of the way. Let's get to the golden showers. No, let's get to the code because That's where the money shot is at. Let's do our little ritual. We're gonna sync up with the GitHub, and then we are going to create a new branch. Where is it? New branch. We're gonna go to origin SSE Bloom, create that branch. All right, so we got our new branch. Chili cooked it up just for you. I'm gonna try not to burp directly into the microphone as I go to game.cpp. So not much has changed in terms of the behavior. In fact, if I've done my job correctly, there should no longer be any difference between the SSE code and the non-SSE code, which is what we had in the last episode. So let me start without debugging here. Here's what it looks like. I've tweaked some of the values. I've made the bloom effect look a little different on the wall. And let's see. Okay, I got my controller working. By the way, if the program crashes, it might be because you don't have a controller hooked up. And the game right now, I didn't set it to actually check to see if there's a controller. It just assumes there's a controller and starts calling functions, contingent on that assumption, and crashes if there is no controller, which is really bad, but we'll fix it later. For now, just know that if you're crashing and you don't want to be crashing, you probably want to comment this out. And there's one more line in the game screen you got to comment out that actually does the updating from the gamepad. Comment out those 2 lines and then you're good to go. Or you could buy a gamepad. I mean, shit, gamepads aren't that expensive, are they? I don't know. Go on eBay. eBay that shit. Okay, so the thing works, and it's taken a long time to make it work and to make it look perfect and to make it look exactly like the non-SSE code. Now, the question is not what it looks like. How do you do? How do you be? Where's my code? Where is my code? It's in Surface, right? All right. No, it's not in Surface. It's in Bloom Processor, which is right. Fucking code. I can never find the source file that I'm looking for. Okay, we got a lot of bullshit here. First things first, we are going to collapse the definitions. So, what I've done here is we got a go function here. It calls downsize pass, horizontal pass. This is all the same, but here's the thing. All of the actual functions that implement these passes, these algorithms or whatever, they are in this section here in private functions. Start with an underscore and then downside pass and then SSE3 or x86 or whatever. Now what I have is I've got these 4 function pointer member variables. They point to functions. Just point to functions. And what I do is I bind the function pointers to these private functions depending on what kind of instruction set I have. So I've got this class. It's called instruction set. And I think I talked about it in the SSE series. I hope I did, but I can't remember. But anyways, it is found... where is it now? All right, here it is. It's in cpuid.h, so it's not in a file called instruction set. Kind of misleading, but it's here. It is here. So, so this class here, what it does is it allows you, it's basically a wrapper around the CPU ID instruction, which can be called with the CPU ID intrinsic. And what it does is it gets the CPU ID information. It gets what kind of CPU you have and also all of the capabilities of the CPU, what kind of instruction sets and other bullshit that it supports. So we can use this to distinguish between a CPU that supports SSE3 and one that does not support SSE3. That's a mouthful, which is, SSE2. I'm basically assuming that everyone is using SSE2 because that's been standard since like 2004. I'm just pulling that number out of my ass. I don't know. 2002. I have no idea. At any rate, it's been around for a goddamn long time. And if your computer does not have SSE2, what are you doing with your life? So we assume SSE2 and we check for SSE3. We bind to our member function pointers depending on, what we have. And there's also a switch for use SSE. That's just a define that you can use to disable SSE altogether, and then it just uses the standard non-SSE functions. Now, we just pass it a pointer to initialize the member function pointers. We initialize it with just the address of the member function, but we have to wrap it with this mem function wrapper thing from the standard library. And the reason is normally according to this standard, we should not have to do this, but apparently this is a bug in Microsoft Visual C++. So we got to put this little wrapper around it to be able to make this downsize pass function object point to this member function. So you gotta do it. It's just what you gotta do. So that is how we can dynamically bind these function calls to our actual concrete implementations of the functions. That's how that dumb bullshit works. And then you just call go, and it calls these 4 functions, which call the function pointers. When you have a function pointer to a member function, you got to pass it a pointer to the object that it's working on. So that's why we have this pointer in here. You got to do it because member functions, they've got to be associated with a particular instance of the class that they belong to. That's just common sense. Water break. Now we get to the actual stuff here, which is our 4 functions. Like I said, I'm not going to explain the original algorithms. That's in another video. So let's get down to the SSE implementations. So this thing is you're averaging 16 pixels together to downsize the pixels so that we can blur and then upsize, because it's faster to perform the blur if the pixels are all downsized. So what we're gonna do is, what do we got here? So what we're doing is we're loading in 4 rows. Each row contains 4 pixels, right? So we load in the 4 rows. Let's go on to a diagram, because visualization is a tool that we can use. Let's not look at this one. Let's look at this one. All right. So you got 4 rows. Let's say the yellow. Why do I have... Never mind. Whatever. It doesn't matter. So let's say I've got these yellow pixels. They're from our original back buffer that we're going to perform our bloom on. So here you got your 4 rows. So your starting pointers point to these pixels here. These 4 here. And we're going to take these 4 SSE sized rows and we're going to add them all together and divide by 16. And we're also, this is downsize and, let me see here, downsize pass. But what it also is doing is it's scaling those values by our X value, which is bloom. It's not alpha. We're using, you have X RGB, right? In this case, we're using the X not for alpha, but for how much bloom that part of the image is going to contribute, that pixel is going to contribute. So we got to scale by X, and then we average all of those results. So what I've done is I've packaged together the code for processing a single row, a single group of 4 pixels in this lambda function here. I like to use lambda functions to package up my stuff. And so what we're doing here, very simple. We unpack the pixels to 16-bit channel values. So we got to use two 128-bit registers to hold them, the low 2 pixels and the high 2 pixels. Then we broadcast the bloom value in the same, to all channels in the same pixel. So what this is doing is it's just taking the X value and it's moving it into all of the positions. I guess I could quickly explain how that is actually done. Shouldn't be too painful, should it? Let's look at the code. So what we're gonna do here is first we're doing shuffle low and then shuffle high. Well, I mean this is basically common what we did in the alpha blending for the SSE series. We're just broadcasting the alpha channel, in this case the bloom channel, into all of the positions so that we can multiply vertically with the original value. So now we multiply the color channels by the broadcast's bloom channels. Then we divide by 16, and then we add the high and the low. So what this does is this gives us the high and the low pixels added together. So it gives us basically, so what we're doing here is we are scaling these 4 pixels, and then we're adding this and this, and we're adding this and this for every single channel. So we're getting 2, so we're getting 2, I can't really say pixels worth, but basically this is going to be the low 64 bits, and this is going to be the high 64 bits in the result. Just the sums of these 2 pixels and these 2 pixels. Right. Now, and that's all you're doing for a single row. And then what you're going to do is you're going to, of course, you're going to load the rows. This is just figuring out the calculating the pointer start addresses. And then you're going to load the rows, and then you're going to process the rows and accumulate those results. So sum is equal to the first row, and then you add the second row to that result, and then you add the third row to that result, and the fourth row to that result. And then, because, like I said before, you've got 2 sums in the high and the low 64 bits, you're going to shift one of those over by 64 bits, by 8 bytes, and then add them together. And that's a shift right. So now the sum of all 16 pixel channels is going to be in the low 64 bits. Then you're going to divide by 256, right? Because we divided by 16 up here, which covers the fact that we're summing the 16 pixels together and averaging them. So you got to divide by 16 to take the average. But you also have to divide by 256 because we multiplied by the bloom factor. So the bloom factor is scaling, so you multiply by bloom and then you divide by 256. That's what you do here. Then we pack them back into 8-bit channels. So you'll have a 32-bit pixel value. And this just converts that value from MMX. It'll convert the low 32 bits into just a standard 32-bit value, an int. And then we store that in, Pout, which was initialized to our buffer that we're going to be using for the next stage, which is the horizontal blur, I believe. Yes. So that's it. That is all she wrote about the first one. That's the easiest part. It gets harder. Now, the SSE 3 version is the same, only instead of doing that shuffle low, shuffle high bullshit, we do it all together with what is it? P-shuff-B, the shuffle EP8. And that is better for 2 reasons. First of all, you're replacing 2 instructions with 1 instruction. And second of all, the original version, it takes the unpacked result and then shuffles that. This version works directly from the row. So these operations don't depend on this result. So you've got less of a chain of dependency. So you get more instructions working in parallel. And the rest is the same. It's exactly the same bullshit. So this one just takes advantage of P shuff B. All right. Next we have fun times with horizontal pass. I'm going to go... Which one should I go first? I think I'm going to start with the SSE 3 version, maybe. Nah. Start with the SSE 2. Alright, so we've got a lot of bullshit to talk about here. Basically, it's working the same as what we had in the just in the standard scalar version. So you've got, I should really get a new image here. I'm going to go to layer 1 here. That isn't what I wanted at all. We're going to add a new layer, layer 2. All right. So let's say you've got your standard image. How should I lay this out? And you're going to want to do the convolution with the kernel. So you're going to have 16 pixels here. This is your input. And you're going to have a bunch of pixels here. And you're going to take the convolution here. And that'll give you this result pixel out here in output. So that's fine. So this is going to be 16 pixels. So you load 4 SSE registers. And then you're going to multiply those by the values in the kernel. Multiply those values by the values in the kernel, add them up, divide by something, and that gets you your output. But the problem is that the next one, the next value here, you're going to have to work with the values from here to here. Input 2. But as I've mentioned before, you can't directly load these unaligned addresses. You have to load aligned to every 4th pixel, right? 16 byte alignment, or 128 bit alignment. Yes, that is correct. Now there are, as I mentioned, there are instructions to do unaligned loads, but if it's possible, it's faster. It's always faster to do aligned work, unless the fixing up that you have to do ends up being slower. And also, it's going to be extra work every time you want to process every single output pixel to load in 16 pixels from memory. You've already got those pixels loaded into registers. So instead of reloading all that data from memory, well, basically from the cache, but still from memory, wouldn't you just rather reuse the data that's already in those registers? So that is what we're going to try to do. And the way we do it is, so we've got 4 XMM registers, and they're each filled with 4 pixels. These, altogether, these 16 pixels here. Then you've got these 4 pixels, which are the ones that are going to be processed next. And what you're going to do is call these pixels the deck. These are the pixels that are on deck. And you want to shift in pixels from here into here, and you want to shift these pixels across these registers. And this pixel is going to go bye-bye. That's what you want to do. We have a window a convolution window of pixels that we're going to multiply by our kernel and then sum and then divide to get our output. And we are going to be shifting pixels from the DEC into the convolution window, multiplying by the kernel. And when our DEC is empty, that means that we've done 4 pixels, and then we can load a new DEC until we reach the end of the input line, and then we start on the next line. And that is how we're going to make these babies. So the question is how to perform a shift across 4 registers. And the way we're going to do it is we're going to make I have made a lambda function that takes references to 2 registers and that shifts values from 1 across these 2 registers, from the high one into the low one. It shifts 4 bytes because that's the size of 1 pixel, right? So what you do is, first thing you do, so let's say we've got make another image here. So we've got 2 registers. We'll call this one, So the way I'm ordering them is I'm ordering them the way that they would appear on the screen. So I'm putting the high order on the right side, which is different than when you write the number out in hexadecimal. But just bear with me. Just keep it in your mind that this isn't the normal way that we write values out. It's just that on the screen, in screen space, high is on the right, but when generally, by convention, high is on the left. So it's fucking bullshit, and it messes me up so many goddamn times. W, X, Y, Z, A, B, C, D. So we want to shift this one in here. What we're going to do is, first thing here, we're going to take the carry value, which is this value. This is what's going to be shifted out of high and into low. It's the carry. And what we're going to do is we're going to copy it into a new register shifted to the right. So we're going to basically copy it into another register, copy this high into here, and then shift it to the right by 20, how many bytes? By 12 bytes. And that'll put W in the high part. Remember, high is on the right. Today, right now. This is called the carry. Then we're going to shift this one left. So the result of that, oh wait, no, don't be stupid. We're going to shift it right. And shifting right is going to move to the left because, remember, we're writing this backwards from convention. So this is the left shift, but because the high order bytes are on the right side, which is opposite, on my drawing, shifting to the left, but it's a right shift. Trust me, it's a right shift. Okay, X, Y, Z, 0. That's the result of this operation. And we're also going to shift this to the right by 4 bytes, and we're going to get B, C, D, 0. Then we take the carry, which is conveniently in the high position, and we got an empty position in the high position here. We're going to OR this into this. We get B, C, D, W. So now our result is B, C, D, W, X, Y, Z, and null, 0, which is a 256-bit shift to the right, which is moving to the left in our diagram, because our diagram is using the screen space ordering. There you go. So that is your 256-bit shift in a nutshell. Now, what you're going to want to do, this is what we're doing here. So we copy into a different register and we shift left by 12. Yes, Wait. Shift left by 12. Yeah, that's correct. Let me make sure. Yeah, it's moving to the right on our diagram. That means we shifted to the left. Okay. Then we shift right by 4 in the D word, and then we copy from high to position in low. Now remember, I said we've got to I said we got to shift the low to the right, do a right shift by 4, but I didn't do that in here, and the reason is because we're going to chain these operations together. So we're assuming that the low bit is already pre-shifted, and this allows us to chain multiple ones together. You'll see what I mean in a second. So we assume that the low one is already shifted to the right, and thus we can directly OR the carry into the low XMM register now. Oh, yes. Here is what that all looks like together for the 640-bit change shift. We pre-shift source 0, and then we do shift 256, shifting 1 into 0, shift 2 into 1. Remember, part of this operation has already shifted 1. So now 1 is pre-shifted because it was participating in this operation. So now 1 is pre-shifted. We shift 2 into 1, 3 into 2, and then we shift pixel from deck into 3. And that's how you perform the change shift. So what you're going to do is you're going to set up your input pointer, your end condition pointer, that's the end of a line, and these are all calculated based on y. Y is just looping on coordinate, but in the line, we want to actually, in every single row, we want to loop by pointer because it's faster to just increment the pointers rather than to recalculate the indexes based on coordinates for every single group of pixels that we process. So we set up our input and our output pointers. Remember, input is going to be MMX stuff, but the output is a single pixel, so we're just using a standard color. Standard scalar value pointer. Then we're going to preload the input pixels for the convolution window. Then we're going to load the deck, and this is inside of the loop for the row. And this loop is going to run for every group of 4 pixels. Preload the deck, and then for every pixel in the deck, we're going to process 8 pixels. Process 8 pixels. So these are the 8 pixels of the 16 pixel convolution window. So source 0 and source 1, and then source 2 and source 3, and you add those results together. And then again, you're going to shift and sum, and then you're going to divide, and then you're going to pack, convert, and output. Now, the reason why we do the convolution in 8 pixel groups is I think mainly because the coefficients, we're unpacking them to 16-bit values, so we can only handle multiplying by 8 pixels at a time, right? If the coefficients were 8-bit values, then we could handle 16 of them at a time, but because they're 16-bit values, we can only have 8 of them in a register. So we use the coefficients to process the low coefficients to process the low 8 pixels, and the high coefficients to process the high 8-bit or 8 pixels. Now, here is our process 8 pixels and function thing, lambda. So we got a sum for accumulating the high and the low accumulations, if you will. So what are we going to do here? We're going to process the low pixels of source low. So we unpack the source pixels. Now what we've got to do is, okay, so what we have, let's It's time to get visual. And I'm not talking about Duran Gray. What we got is we've got a we've got, wait, which one is, this is going to be low and this is going to be high. So we've got a register and it has our 8-bit coefficients in here. Coefficient 0, 1, 2, blah, 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 blah. We unpack it into 2. So we unpack the first half into here and the second half into here. And now we've got 16-bit coefficients. 1, 0, 1, 2, blah, 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 blah. And here we've got 8, 9, blah, 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 blah. These are 16-bit values. So there's only 8 of them. Here we got 16 of them. We got these coefficients. So we're going to unpack 4 pixels. So we've got, for example, SRC0. Unpack that to SRC low, SRC high. And this is going to have 2 pixels, each with 4 16-bit values. So now we've got 16-bit values in here, 16 values here, and our coefficients are also 16-bit values. Now what we want to do is we want to multiply, for example, for source low and source high. For low, we want to multiply this one, these channels by 0. This one doesn't matter. It's just, it's just our, well, it was our bloom, but now it's not used for anything. But anyways, we want to multiply these channels by 0, these ones by 1, these ones by 2, and these ones by 3. So we've got to go from our 0, 1, 2, 3, 4, 5, 6, 7, and we got to broadcast those such that we have 0, 0, 0, 0, 1, 1, 1, 1, and then 2, 2, 2, 2, 3, 3, 3, 3. And that, my friends, is what this bullshit is doing. So we shuffle low epi 16. And what this does is this copies, remember, this is the low side now, because now we're not in screen space, we're talking about conventional. So this is low, this is high. So in the low 16, now our shuffle low, epi 16 can only work in the low 16-bit, or 64 bits. So here in the low 64 bits, the 16-bit values are going to be coefficient 0, 0, and then 1, 1. Now, so the 32-bit value here in the low is going to be 2 zeros side by side. And the 32-bit value, the high 32-bit value of the low 64 bits is going to be 1, 1. Now we're going to shuffle those 32-bit values, which contain 2 coefficients, the 2 of the same coefficients side by side. And we're going to shuffle them so that these 2 are duplicated here and here, and this double is duplicated here and here. And that will give us 0, 0, 0, 0, 1, 1, 1, 1. That's basically the idea, how you broadcast those coefficients into the right places, and then you multiply and you shift down by 16. You've got to do a little bit of pre-division here, because if you don't, you might have a chance of overflowing, because you're adding 16 things together. So pre-dividing by 16 will ensure that you're not going to overflow, regardless of your coefficient or whatever. You might even flow, but you'll never overflow. Thoughts arrive like butterflies. All right, now what we're going to do here is we did the low. Now we're going to unpack the high parts of source low. And then we're going to broadcast again. Here we're going to be doing coefficients 3 and 2, and then we're going to broadcast those doubles in 32-bit doubles into their positions, multiply, And this one, we were just setting the sum, but here we got to accumulate. So now we divide, and then we add that to the previous sum. And then we do again the same thing, but for source high. And now we're doing shuffle high because we're going after the higher coefficients. So it's a little bit of a different game, but it's the same idea. And we do the same thing here, and then you're done. Bob is your uncle. You do that once for the low coefficients and once for the high coefficients. And then you've got all your stuff multiplied and summed up together here, and then you do like I said, and you're all done. Now, the final row is a little a special case. I don't know. Honestly, I don't know why the final row, except that the only reason why I could think of pulling this out is because in the final row, you don't have to do this extra shift. So the reason I pulled it out was to basically just micro-optimize here, cut out this final 640-bit shift because we don't need it. That's all I can think of. Anyways, that's SSE 2. SSE 3 for horizontal shift is about the same. The 8-pixel processing is the same exactly. But the 640-bit shift, we don't have to do the shifting and masking. We can use the align R instruction to basically do the same thing, to concatenate two XMM registers and then to shift it and get a single 128-bit value. So align R will give us a little bit of a speed boost, not that much, but enough to justify the existence of adding this variant. And yeah, that is basically it. I'm going to say everything else is the same bullshit. All right, now the horizontal pass, wait, no, I just talked about horizontal. The vertical pass is a bit of a different beast, because as you have noticed, loading pixels, wait, let me just get rid of this. Add another layer. All right. So loading pixels from memory, if you do an SSE load, you're going to load 4 pixels like this horizontally. Now, if we wanted to apply the same algorithm to the vertical blur, we'd have to load 4 pixels like this. That is not possible. It is possible in AVX with a scatter. I'm not sure if you can do a scattered load gather operation, but there is scatter and gather. But either way, it's slow. You don't want to be low. You want to be loading values that are in adjacent memory locations. So this is not going to be a thing. You're not going to be able to do this vertical operation or this vertical streaming with SSE directly. So the question is, what are you going to do? Now, originally, I had an interesting solution to this problem, basically. What I did was you do your horizontal processing like this, like normal, using the algorithm that I just shown you. But what you do is when you output the pixels, you actually transpose the image. So now, if this is your starting point here, your starting point is going to be here. And you're outputting the pixels like this. So the horizontal operation will run like this and output the pixels like this. And now, because your image has been transposed, what you can do is you can perform the same horizontal operation on this, and it is effectively a vertical blur because you're working on the transposed image. And when you output from this one, you output transposed again, and you're left with your original image or your original orientation. It's been blurred horizontally and vertically now. And I did this and it worked great. But I figured I'm going to try something a little different. I'm going to use two different algorithms for the horizontal and the vertical. And I'm not going to do the transposing bullshit because it's kind of mind-bending in a way. So let's talk about the vertical pass. And we're going to start with the SSE 3 version first. Basically what we're doing, let me just quickly look over this to refresh my memory. It seems like a very short algorithm, and it is. What we're doing is, let me just go back to my algorithm. Instead of like in the original, we have a 16-bit horizontal window. We load 16 pixels, we shift in. We're not going to do that. What we're going to do, since we're working vertically, we're going to load and work with 16 vertical slices. Vertical slow rise slices, each having 4 pixels each. And we're going to load them. And we're going to multiply them. So this one is going to be corresponding to, what is it? Coefficient 0. This is 1, 2, 3, 4. So we load these 4 pixels. We multiply them all by the same coefficient. And the same here and here and here. And we accumulate that. And then we store the result right here. There's going to be 4 results now. We're generating 4 results at a time. So before it was a horizontal blur, and we were using a horizontal operation to do it. Now we're doing a vertical blur, and we're going to use a vertical operation to do it. So we load, multiply, and accumulate for 16 rows of 4 pixels each, and then we store the value here. And then we start over at the beginning, and we reload all of these memory addresses again and process them. One extra here. This is the new one. And this time with, the coefficients shifted over by 1. And then we store that result in here. And again, so we've got a loop that is looping through these column sections of 4 columns each. And then we've got a loop which is looping through start sections. And then we've got inside of that loop, we've got a loop that is looping through the 16 rows in every window. And the loop outside of that loop is looping through the start of the window. And the loop outside of that loop is looping the start of the window loop. So it's looping through the columns. If that makes any sense whatsoever. So here we've got column pointers that point to the start of a column. We've got the output column pointer that points to the output. And we've got the row delta. And this is what? Column pointer in is just a fringe. This is fringe plus. All right, so this is just the difference between. Let's go back here. This is just the difference between 2 rows. So this is what you add to a pointer to get basically one down from the current coordinate. Column pointer end. So this is the end of a particular column. And then what are we? We're looping through column pointer in, column pointer. Is that really what we're doing? I think column pointer end actually points here. So when the column pointer reaches here, nothing here, that means we're at the end of the process. the end of the whole shebang. So what are we gonna do? So row delta, column pointer out, which is the output. Now notice here, and I didn't mention this, but also in the horizontal pass, we've got to take into account the fringe. That's the section of the image that we drew extra that is not going to be part, it's not going to have a corresponding part in the output. So this is the whole thing. No, this is the whole thing. But this part here is the fringe because, I mean, if we tried to output values from here, the input would have to read into memory that doesn't exist. So we have this fringe to enable us to give us enough data at the edges to be able to, you know, generate some output. I've explained all this in the previous video about the fringe, so I'm not going to beat that dead horse, but just know that it's something that's here. All right. So yeah, we just looping through columns, and then we are looping through rows in a single column, and then we're looping through actual single, you know, 4 pixel sections in a single row. So this row pointer, this loop here is moving the window down. This pointer here is moving from column to column. This is moving the window within a single column. And this one is moving inside of a single window. And inside of that window, you're going to process. And you're going to generate sums. Now, with 4 pixels, so you're summing up in 16-bit values. So you're going to have high and low sum. So sum low is going to be the first 2 columns of pixels, and sum high is going to be the last 2. And you pass in the coefficient and coefficient mask, which I will explain in a second. And it's going to do, like I said before, it's going to multiply the corresponding coefficient with all the channels in that 4 pixel chunk and accumulate into sum low and sum high. Cream of some young guy. So how does process work? This is the genius part of the situation. So what we're doing is we basically need, 16 different masks in order to do this bullshit. So one of the masks is going to be, all coefficient 0, and the next one's going to be all coefficient 1, all coefficient 2. But all those different masks take up registers, and we only have a finite amount of registers. And if we have more, more XMM sized data units or variables in flight than we have registers, we're going to have register spilling, and it's going to, the CPU is going to have to, temporarily store registers into memory, and so that it can load other ones and work with them. What we would like to do is we would like to be able to have it to work all, as much as possible, all just within the CPU without having to load and store from the cache. L1 cache access is fast, but it's not free. So, in order to do that, I've devised a little scheme wherein, so you've got a register that holds the coefficients, and these coefficients are packed into byte values. And then you have a shuffle mask that will unpack those values into 16-bit values. So this mask here, if you can see, this is the high byte and this is the low byte. So it zeroes out the high byte, and then it shuffles the 0th byte from the source into the second highest byte, and then it zeroes out the third highest, and it shuffles in 0. So this is unpacking and broadcasting the low byte of the source into all of the 16-byte values into here in the destination. So this will get us our first coefficient unpacked and ready to multiply. So you pass in coefficient mask, and you got some high or some low, and your pointer to your input. You're going to load your input in, which is going to be, you know, one of these deals, 4 pixels. And you're going to broadcast your coefficient. You're going to broadcast your 0th coefficient into all the positions. And forget about this because we'll talk about it later. This is the secret sauce. And then you're going to unpack the low of the input. You're going to multiply it by the coefficient mask. Then you're going to divide and add, and then you're going to unpack the high, multiply, pre-divide, add. Now the secret sauce comes here. So this mask can be used to unpack coefficient 0. But what the next time we call the process, we're going to want to unpack coefficient 1, because the next time we call process, we're going to be processing this package of pixels, and this one needs to be multiplied by coefficient 1, the next coefficient. So what we do is we have mask delta, which is just a bunch of 1s and 0s here, and we add this to this, and that will increment this value here, these 0s, so there'll be 1. And these 0s here are the values that determine what we're pulling from the, what we're pulling from the kernel and broadcasting. So after we add the delta mask, the mask delta to the mask, now the mask will be for broadcasting coefficient 1. So the next time we call this function, it's going to broadcast coefficient 1 and multiply it, and add, it's going to increment these values. Next time, coefficient 2, coefficient 3, 4, 5, 6, blah, blah, blah. So first thing we do when we get into the loop for a window, a convolution window, is we set the window pointer up. We set the end of the window pointer. We initialize the sums to 0. And wait a minute. Oh yeah, and here's the thing I was actually trying to talk about. We initialize the coefficient mask to the start, which is broadcast coefficient 0. Then as we call process, the coefficient mask is incremented so that it broadcasts coefficient 2, 3, 4, 5, 6. And when we reach the end, we leave this loop, come back out, and when we come back here, we reinitialize it back to coefficient 0. And that is the beauty of the mind of Chili. Now, SSE 2, unfortunately, we don't have the motherfucking p-shuff-b instruction. So we gotta do things a little more gangster style. So what we do is we've got these convolution step vertical blur, which basically corresponds to the process lambda function that I had before. And what we're gonna do in here is, this is a macro. So this is expanded at compile time into this code. And the part down here is basically the same as the stuff in the SSE 3 version. But the broadcasting of the mask is going to change because we're going to have to do it without our good old friend, Mr. p-shuff-b. So what I do is I've got these, if statements here, and this macro takes an index parameter, which is the index into, which coefficient we want to broadcast, and it checks to see if we want to broadcast the high half, the high 8, or the low 8, and then if it's the high 4 or the low 4, and depending on which ones we choose, it's going to use shuffle 16 and 32, basically the same thing that we had for one of the previous ones. I forget which one. I think it was for the horizontal. Same idea there. We're going to do it here. Now the trick is, because this is a macro, this code is all going to get expanded. So if this index is a compile time constant, this value, this if statement result, is going to be known at compile time. So the compiler will actually, it will optimize out all of these branches. So this is not going to be branchful. I mean, if this were a standard function, this would not be a compile time constant. And the compiler probably wouldn't be able to optimize this out. So you'd have, 2 branches for every call to this. And the branches would be different a lot of the time. They would work in the same pattern, but I'm not sure a branch predictor would be able to pick up on the pattern. Maybe it would. At any rate, because this is, well, here we do it here. Because we have to make this a compile time constant, I can't put this into a loop. So I've got to actually copy out the line 16 times, gangsta style here, incrementing the row delta every time. And that allows me to put a compile time constant as one of these parameters, which allows the compiler to optimize out these branches, and it just selects one of these pieces of code to actually execute. And so it executes the proper sequence of unpack and shuffle to get the what is it called, the coefficients all in the right space, and then it executes the unpack, multiply, divide, and accumulate as per the SSE3 version. Everything else basically the same. So that's that. And I would just like to mention that this is another way of handling writing SSE subfunctions so that they're, inlined and optimized properly. I prefer using lambda functions, but if you have a value that has to be a compile time constant, macro is another thing that I often used. These days, I prefer to use templates. So in templates, the thing that has to be the compile time parameter, the compile time constant, or immediate value, you put that in the template parameter, and that allows you to pass in a compile time value into the function effectively. Later on, C++ 11 supports something called const expression, which should allow you to make a function and pass in a compile time constant. But the current environment that I'm using doesn't allow that. It doesn't implement that feature of C++ 11. I'm using Visual Studio Express 2013. Not implemented yet, but it will be soon, and that'll probably be the best solution. Until then, your next best is using the templates. And if you can't use templates, or for whatever reason you don't want to, you can always default down to the ugly macros. All right, so that's downsize, horizontal, and vertical all done. We've got one more to go. I think I can get this done within an hour 30, which is as good as I could hope for, basically. All right, so the upsize blend pass. Now this, as you may have known, or you may know, was freaking long and full of bullshit in the x86 version, and it only gets worse from here. So let us look at the SSE3 version of this. There's not much difference between this SSE3 and SSE2, but we'll do it. We're gonna do it up. All right, so I'm assuming that you've already watched the previous video and you understand how this works. So I'm just gonna have to talk about how to do it in SSE. So we want to generate from 4 input source pixels, we want to generate 16 outputs. Where is it? Here it is. So the red ones are the input pixels. The yellow ones are the outputs. And I can't write on this. Unusable. So we're generating in one general step, we're generating these 4 pixels here. Now the question is, what do you do with these pixels on the outside edge? And the answer is, you basically just clamp them to their nearest input pixel. So these ones here are going to be just this pixel value exactly. And these ones here are going to be blended between these two. So how do we do that? Well, the way I handle it is I break it up into 3 sections. The first section is the top 2 rows of pixels. And they are handled, let me just undo this quickly. They are handled with upsize edge in non-intrinsic lambda function. So what we're doing here is we load in 4 input pixels, and what are we doing here? Old pixels, shuffle in 4 blah blah blah. Yeah, it's kind of complicated. We've got a loop. It's weird because we got a loop here, a while loop, but we have to jump out of the loop in the middle of the loop. It's weird how I set that up, but it was the best thing I could come up with at the time. So what you're gonna do, we're gonna call this generate gradient. So I guess I should explain that. This is just to interpolate horizontally between the low 2 pixels of the input. So what it does is it takes a register, and the register is 4 pixels packed 8-bit channels each. And what it's going to do is it's going to interpolate between the low 2 pixels in that XMM variable size register, whatever you want to call it. So it unpacks the low 2 pixels, and copy the low pixel to high and low 64 bits. So this, what does this do? Right. So what this is doing is it's duplicating the low pixel in the high and low 64 bits. Then multiply input by, so now we have the low pixel duplicated twice. Multiply input by decreasing coefficients. Okay. So gradient coefficient. This is the coefficients that are used to multiply the pixels. So when you're generating the gradient, when you're going from one pixel to another, you're going to multiply one. For example, you're going to multiply the leftmost, let's say, by 224. And the next one you're going to multiply by 160. And that is the... Right, so you're going to multiply the left one by 224, and you're going to multiply the right one by the complement of that, which is, I don't know, probably 32. Right, 32, and you're going to add them together. And this one is going to be 160 and 96, and then it's going to be 96, 160, and then it's going to be 32 and 224. So this is explained in the other video, so if you need to, you got to go back and watch that. I don't want to go back and go over too much bullshit. So here we are duplicating the low pixel, multiplying it by decreasing coefficients. So multiplying by 224 and multiplying by 160. Then lower pixels. For high pixels, right, so this is for the lower output pixels. So lower output pixels are going to be taking most of the low pixels. So we're copying the low pixel into here, multiplying it by the coefficients. Now we're reducing these coefficients by 128. So now it's going to be 96 and 32, multiplying it again by the low input pixel. And so now what the result of what we get, this would greatly benefit from a picture. So we've got the input, and it's got pixels A, B, C, D. This is low, this is high. First thing we do is we unpack this. Wait, I don't want to take up that much space. We unpack this 16-bit channels, A, B. All right, now what we're going to do is the goal is we want to generate 4 pixels from these 2 pixels. And the 4 pixels are going to be a blend between A, B. We're going to have A and a little bit of B, more A, smaller B, smaller A, bigger B, very small A, very big B. You get it? So as we go from low to high, we're getting less A, more B. So to do that, we go A times some alpha values, not alpha blending, but you get the idea. A times alpha plus B times 1 minus alpha. And then more, but this alpha keeps getting smaller and smaller as we go along. So to do that, first we generate the A's, the A times alphas. So we duplicate this to AA, and we multiply by, alpha 0, alpha 1. And then we do the same thing here, duplicate AA, multiply by alpha 2, alpha 3. And alpha 2 and alpha 3 are derived from alpha 0 and alpha 1 by adding 128. Now I've created a little function here to generate 128 for me without loading it from memory. So this is a fast way of generating 128, and that's right here. And so what you do is if you compare any value with itself, the result is always going to be all ones, because anything compared with itself is going to be equal. And when you do compare for equality epi16, if any two 16-bit values are equal, the output in that position is going to be all ones. If they're not equal, they're going to be all zeros. So what this does is it puts all ones in the entire XMM register. Then you shift right by 15, and that will put only a 1 in every 0 position for all of the 16-bit packed integer positions. And then you shift left by 7 to multiply by 128. So this will give you 128 in every 16-bit position in the XMM register without loading from memory. So it's fast. I don't know how much of a benefit it is from just loading from memory. Like, for example, just creating a constant here and copying in every time, or just using the constant. Maybe it might be slower. Maybe I'm being a little too smart for myself. But either way, it's probably not going to be a big difference. It's just a fun little trick that you can use. So we subtract 128 from the coefficients to generate coefficients 2 and 3. And then we multiply them again by the input A. Then we flip the coefficients around. So first we copy the high pixel. Now we're working with the B pixel. And we shuffle the coefficients in the opposite direction. And the reason for that is because now we are increasing. So when we were multiplying by A, we were getting smaller and smaller with the A, so the coefficients were decreasing from alpha 0 to alpha 3. Now we're increasing. So we start off with a small value, which was just our alpha 0 and alpha 3, but we flip them backwards. So now they're increasing. And then we do the same thing, but multiplying by the B pixels this time. And in the middle, instead of subtracting 128, we add 128 because we're increasing our coefficients now, our alpha values. Then at the very end, we've got to return the coefficients back to their original state so that they're not messed up for the next call. And we add the low products together and divide by 256. We add the high products together and divide by 256. And then we return the packed value. So because we're multiplying by alpha values, which are fractions of 256, we've got to divide by the fractional part to normalize our values before we pack them back into 8-bit values. And that is what generate gradient does. It generates a horizontal gradient and interpolates horizontally between 2 pixels. It only operates on the low 2 pixels of the input. The high 2 are ignored. Because here we do unpack low, and then we shuffle and shuffle. So we never even look at the high pixels of the input. All right, so what upsize edge does is it generates the gradient between the low 2 pixels of the input and then it outputs that right. So generating the gradient. Let's get out of here for a second. This is the other tricky part of this stupid algorithm. Makes my brain hurt. So generating the gradient between the first 2 input pixels. Now I'm feeling like maybe this is going to be longer than an hour and a half, and it pisses me off. So the gradient between these two is going to generate these pixels here, these ones and these ones, because they're the same. We're clamping. So this row is the same as this one, and it's the gradient between here and here. But that doesn't give us these pixels. These pixels here are just this pixel itself. Now the interesting thing is basically we are out of phase between our input and our output, because our input loads these 4 pixels here. But our output, we want to store those pixels correspond to these 4, and these 4, right? But that's out of phase because here we're loading from the start of a row, but here we're starting 1 pixel in, 2 pixels into the row, or 3, and depending on how you're counting. So the first thing is, we can't take this result and store it here because we're out of alignment. The second thing is, what do we do about this bullshit here? The answer is, we prime the pump with those pixels. Basically, we just take the input pixel and we broadcast it to all 4 parts of a value. We store that in something called old pix, and what we do is we concatenate old pix and new pix together using the p-align-r instruction. So we slam the half of the old pix and new pix together to generate the output, and then we add the output to what is already on the output here is the actual back buffer, the full-size back buffer. So we're adding this with saturation on top of the old back buffer. This is adding the bloom effect onto the original image. And we're doing this for the top row and the bottom row because they're the same. So the output, the bloom part is the same because we're clamping, right? Here and here. But the actual original pixels are different, so we're adding to different points. So yeah, we're taking these values here. We're basically taking a register that's just this pixel copied 4 times, and we're taking a register that is the gradient of these 2 input pixels, and we're slamming those together, taking the middle of that slammed together result and storing it into memory here. So this is old pix and this is the new pix. We slam them together, we store. Now, this interpolation result, this gradient, goes into old pix. This is new pix. We slam them together, take the middle result, and that is stored here. And then this becomes old pix. This is new pix. Slam them together, take the intermediate, the middle parts, stored here. So we're just taking the old and the new and slamming it. Now in the beginning, the very first one, we don't have old, so we clamp this pixel, call that old pix, and that's how we prime the pump to get the thing started. And that's what we're doing here. And we do that, and we're checking to see if we reach the end pointer, the end of the row. And if we do that, we jump out. Because the very last part, it is going to actually load the new row in and do a bunch of bullshit. And we don't want to do that if we're at the end. So we do this bullshit, and we jump out if we reach the end of the row. Now in the right corner, it's a special case, right? Because now we're clamping to the right. That's why we got to jump out early. The last section of pixels contains the right corner, which is clamped to the last pixel. So you can't load new pixels in because there are no new pixels. The row is ended. You've got to clamp to the last pixel. That's why you've got this weird loop that has a while true, an infinite loop with a break condition in the middle. I'm sure there's a way to reformulate it, but this was the easiest for me to do. And that is how you generate the top edge. Now, the do line function, this generates the top and the bottom 2 rows. The middle rows are done in the do line function. Now the do line does basically the same as what am I trying to say? It's the same idea as the vertical, but now, so with the top 2 lines, we were only interpolating between, let me just get rid of this bullshit. I'm gonna do this, I'm gonna do this, I'm gonna do this, I'm gonna do that. There we go. So the top one, the edge case, we're just interpolating between, these 2 or these 2. We're interpolating between the top pixels of the input and generating the top 2 rows of the output. But in the general middle case, what we're doing is we're interpolating between 4 input pixels by linear interpolation. So interpolating in 2 dimensions to generate 16 outputs. So what we've got to do is we've got to interpolate between the horizontals here. That'll generate us 4 top and bottom interpolation rows. And then vertically, we interpolate between these ones to give us 4 columns of 4 pixels each, 16 output pixels in total. So we got to interpolate twice, once horizontally, once vertically. Horizontal interpolation is going to be, we're going to reuse the generate gradient function, the lambda. But for the vertical part, we're going to use vertical gradient output, which calls generate gradient. And this function, this lambda function, takes input pointers to the 2 input rows and pointers to the 4 output rows, and it reads the input pixels, generates the gradients, and then adds them and outputs them to the output. So you generate the horizontal gradients for the top and the bottom, which are just the input, calculated on the input and the output values. Now this part is a little tricky, and it's another little wily chili trick here. What we're going to do to generate the vertical gradients is we're going to generate them without even unpacking from 8-bit values. So the way we're going to do it is we generate the gradient between here and here and here and here. That gives us, Control Z, that's going to give us, you know, these 4 pixel values here. Now to generate that's the horizontal gradients. Now to generate the vertical gradients between here, what we're going to do is we are going to take the average of these 2 XMM register values. So that'll take the average of these 4 pixels independently. So if we take the average between here and here, we get a value which is halfway between. Then if we take the average again, we get a value that is 1/4 between. Then if we take the average again, we get the value 1/8, which is the first pixel. Then we take the average of these 2 to get this one. The average of this one and this one will give us the 3/4, and then between these 2 will get us this pixel, and these 2 will get us this pixel. So taking the averages will allow us to do this without all of the multiplying, unpacking, and dividing. And it is fucking fast, let me tell you. Way faster than the alternative. So we take the half address, add the half average, and we get the first quarter. And then we generate the first 1/8, and we add that to the back buffer. And old 0. We're using the old thing again. Remember, we're generating values which are out of phase with our output because we have these things here. So the old values are the thing that we use to create the pump system when we prime the pump and then we can output. So here we're using the align R to shove together the old value and then the new value, which is generated from the vertical gradient. We get the first 1/8, we get the third 1/8, and then we calculate the 5th 1/8 and the 7th 1/8, and we mash them together with the old pixel values and add them to the output. Accumulate on the output with saturation. We don't want to overflow. If we add 2 large values together, we don't want them to add to 0 or to a small value. We want them to clamp to 255. Very important. If you forget that S there, you're going to get some, I mean, you'll get a really freaking psychedelic image, but it's not going to be what you want. And yeah, you just do that for all of those four rows, and that is your motherfucking vertical gradient output. And now you just got your loop here. This vertical gradient output, it is capturing these old 0, old 1, old 2. So we can reference these values by reference, so we can change them as well. Which is what it does here. It's sending the old one to the newly calculated one after you output it. And then do line, it just initialize 0 and 1 here. Prime the pump by broadcasting the input and output pixels, right? Clamping, this is where you clamp to that pixel. And here, this is interesting. So for the main loop, right, so for the first part of the loop here, you've got to, you can't do this inside the main loop. I can't remember. This is priming the pump on the left side. So this is generating those old values that will be used here. Right? This is going to be the priming of the pump, and this is what's going to be slammed together. Well, let me just make it a little more clear. Let's say you're doing the first section here. These pixels are what are going to be generated by the routine, but they're going to have to be slammed together with the old values, and those old values are going to be what is here. And to prime the pump, to initialize these old values to the initial edge case, you use this code here, and that primes the pump. And then in here, you're going to do the stuff. You're going to do the vertical gradient output. Right, because in your input pixels, let me just go back here. Your input pixels, whoa, too far. Just far enough. Input pixels, you've got four pixels like that. So that'll generate 1, 2, 3, and then, 4 blocks if you consider the next one in the continuation. 4 pixels generates 4 blocks. So, where is it? So here you're doing the gradient between 0 and 1, between 1 and 2, between 2 and 3, which are all the pixels in that block. And if you're done, if that's the end, you have to jump out. Otherwise, you do from 3 to 0, you load in the next block into new in 1, new in 0, new in 1. And you're slamming that together with the old in 1, and then again like this. And when you hit the right side again, you have to clamp, so you've got to do a little bit of an edge case there. It's the same idea. And that is it. That is all she wrote for upsize middle cases. And this will, this will process 4 rows of pixels. So it'll process 4 at a time, like this, up until the end. And so then you need a loop right here that loops through all of the middle lines. And it calls do line, and the pointer, the input, is going to be the pointer to the beginning of an input, 2 input rows, and the end of the input row, and in the beginning of 4 output rows. And at the end of every iteration of the loop, you're going to offset the outputs by 4. So it's going to point to this output here, and you're going to offset the input by 1 row. So it's going to point to the next row. So yeah, the first row is going to be 2 rows of inputs here, this row and this row, generating this stuff here, and the next one is going to be this row and this row, generating this one here. And in sandwiching these, or this loop here, you've got the top edge and the bottom edge. Here we're just calculating all of the starting pointers for the loop here, and you got to calculate. You got to keep in mind the fringe, so the top fringe and the side fringe, because you don't want to be processing stuff that's not going to be on the end image. Yes, do bottom line, and that's it. That is it. Motherfucker, that was a pain in the ass to explain. And SSE 2, luckily, is the exact same thing, only you don't have p-align r. So what we use instead is this template function, align right SSE 2, and the p-align r alignment immediate constant is passed in as a template parameter. And then the 2 registers that are to be concatenated are passed in normally as functions. And if you go into p-align r, it's just shift left by, you shift one of them right by the shift value. You shift the other one left by the complement of the shift. and then you OR them together. You slam those motherfuckers together. And that gives you the same thing as P-align-R. So that is it. That is all of it. That is everything. There's everything. Oh, I'm broken now. I can't even speak. But that's all she wrote about this optimization. Now comes the fun part, which is to take this baby for a test drive and see how she runs. So just to let you know, it's faster to build in 64-bit versions, run faster. And for SSE, motherfucker, I keep fucking... For SSE, it if you build with support for... What is it? Support for AVX, you're also going to run faster. Now you might say, Chili, you're using SSE, even if you support AVX, you're still generating SSE instructions. True. But if the CPU supports SSE or AVX, you can have VEX encoding for the AVX instructions, and that allows you to have a separate destination. So it allows you to have two sources and a separate destination. So you're not overwriting one of your sources when you perform a calculation, which can reduce the amount of register juggling you have to do and register spilling. So, and there might be other improvements, I don't know, but VEX encoding, if the CPU supports AVX, compiling for VEX encoding, not much faster, but quite a bit faster, like maybe 10% or something. I don't know. Doesn't matter. You can try all this stuff out you want. You can try all the permutations of 32-bit, 64-bit VEX or SSE, standard SSE encoding, and see what works. What I want to do is compare SSE version versus non-SSE version. So we're going to go use SSE false. And that is going to bind these function pointers to the x86 version's implementation. So we're going to build. And we are going to run this motherfucker. We'll just push some buttons. We'll do some bullshit. It's all good. Actually, I shouldn't have done that. Doesn't matter. Let's take a look at the run times. Open in folder, go to Bloom log. So we're looking at about 11.2, 11.4. In my tests without running the CAM software, it was about steady at about 11.2. So we'll say 11.2 milliseconds. That's cutting it pretty close. I've got still a fairly fast CPU, even by today's standards. So for people with lower grade CPUs, it's probably going to be harder to get that to push 60 frames per second. But remember that number, 11.2. Let's set use SSE to true, build it. Run. So now we're running in my SSE3 code. And we'll take her for a little spin here. Not important. And we'll open in here, Bloom log. And now we are down to 1.6, 1.64, 1.6 milliseconds from 11.2 to 1.6. And when I run this without my recording software, it's basically solid at 1.58. So we can call it 1.58. Long story short, it's a hell of a lot faster. And it better goddamn be, because this fucking was a huge pain in the ass to write. So yeah, it's worth it. But you gotta weigh your options. You gotta know when to hold them and know when to fold them. That's all I got to say about that. So yeah, you can play around with the settings, the the code generation settings. You can play around with 32-bit or 64-bit builds. And if you want, you can see how that affects the output. Here's the timer that just times the processing. You can move these and check the speeds of the individual sections if you want. You can go nuts. You can even go into here. If you go SSE 3, if you put in here and false, you can force it to use the SSE 2 versions. And, you can mix and you can match it. It's all the same. It's all good. But that is SSE and how it can help you out in a fairly plausible situation. Like I mentioned before, in general, you're going to use your GPU to do this kind of operation. So this was just an interesting little exercise. But you might do similar operations if you're like building some kind of image processing routine as part of a larger image recognition AI system or something like that. And you might want to do that on your CPU. And if that's the case, you're going to want to use SSE if it's going to be a speed critical thing. But anyways, that's all she wrote about this. I have no more to say on this topic. So next, wait, let me get my thing up here. Next video, finally we can move on to something else, because I'm sick and I like this bullshit a lot, but I am sick and tired of it. So next thing, I've got a few things I'm thinking we might want to talk about. And I'll just put it up here on the screen. I got my notes. Just some stuff to improve the engine, give it some better game feel. These are a little easier topics that will make for shorter videos and less work for me. I want to add a parallax star field so that you can actually know when the ship is moving, even if it's moving parallel to the walls. Maybe add a little thruster, add some sound effects for that, add some music, and I'm going to use MIDI for reasons, because it's going to give me a good excuse to introduce multi-threading with a job system where you've got an independent thread and you've got a main thread, and that main thread queues up jobs to the independent thread that it handles. Other things like a neat particle system for explosions, this will be a little more complicated. I haven't actually started on it yet, but I get an idea. It won't be too bad. Maybe a better looking shield, maybe, I don't know. Just some ideas for what's up next. This is definitely next. The rest, the order is up for grabs. This, maybe not, I don't know. And yeah, it's going to be a lot easier to prepare. And so I can get more content out in the days to come. Now, for the thing that I mentioned at the beginning of the video, I am planning on doing a live stream where I basically mess around doing computer engineering type bullshit. Whoa! Just dropped my controller. So I'm going to mess around, do a bunch of computer engineering bullshit. And I mean, this is stuff that I normally just like to do sometimes on my own. It's not useful. That's not to any particular end. It's just tinkering around that I like to do. So I figured, hell shit, why don't I do this tinkering around and maybe generate some content for people as well. 2 birds, 1 stone. So basically the way I imagine it'll work is, I'm going to be streaming, and people can ask me questions as they're watching the stream. They can ask me questions in real time and maybe give feedback or tell me when I've fucked something up and haven't realized it. And I'm also planning on having someone from the forums, probably Albino Papa, on with me, maybe screen sharing in real time with him, and he can banter with me and he can read chat and also, bring stuff to my attention if I'm busy. That's the basic format that I'm looking at. The 2 topics that I have in mind, one of them is going to be designing a digital circuit system, a CPU, from logic gates, from scratch, from just like AND gates, OR gates, NOT gates. Going from the ground up and building a fully functional CPU that can run a program that we put into it. So yeah, this is the basic idea of stuff that I'm going to be covering, deriving all components from basic logic gates. So I'm not just going to throw down an ALU and say, here's our ALU. I am going to start from AND gates, OR gates. I'm going to build a half adder, full adder, then chain them together to build an adder, and then, make that into the start of an ALU, then add some other bullshit. Everything's going to start from basic principles. Nothing, no jumps. We'll do the data path circuit. We'll figure out an instruction set encoding. We'll make the state machine, the instruction decoder, state machine bullshit. Work on our bus architecture, peripheral, all that good stuff. Write a program in the end. That's one idea of what I want to do. Another thing will be, I've been recently doing private lessons with a guy who watched the videos, a guy from the forums, and I've been teaching him some stuff on the side for money, for making the big bucks. Not really, but, he said he wanted to pay me to teach him some stuff, and I said, shit, man, that's fine with me. So I'm teaching him all about how CPUs work, and to start with that, I've been going over just assembly programming, just real mode 16-bit programming under DOSBox, and I've found that I can't stop, even though I'm almost done with it with him. I want to do more. I want to do a whole bunch of dumb bullshit, and I can't stop myself. So I figured maybe I'll just do since it's not really, I don't want to really make him pay for my my hobby here. Basically, up until a certain point, it's useful for him to learn the assembly, to understand what's going on inside a CPU, and to understand the basics of how a computer loads a program and runs it and all that dumb bullshit. But we're going to move on. I can't keep him there forever because it's not that pertinent to what he wants to learn up until a certain point. We're reaching the limit of what we can do for him in assembly programming, but I want to keep going. That's what I'm trying to say. So I'm going to maybe continue on where I left off from him, but with a live stream. So this one, I'm not going to start from complete scratch. Like for the CPU thing, I'm going to start from the very basics and go step by step. From the ASM thing, I'm not going to start from the very basics. I'm going to start from a certain level of understanding of assembly code and then play around from there. So a little different flavor. And things I'm interested in playing around with are, I want to create a DOS TSR, terminate and stay resonant program. If you don't know what that is, well, you can watch and find out if you're interested. Until now, I've been working in real mode 16-bit. I want to try to basically flip the processor into 32-bit protected mode, which is the mode that the operating system runs in, supervisor mode, and see what I can play around with there. Because you can play around with instructions, 32-bit instructions that you can't use if you're just writing a Windows program, because you don't have the authorization, the authority. You're not running in ring 0. I want to play around with Super VGA graphics and protected mode assembly. Try switching between DOS protected mode or DOS mode and protected mode to call the DOS functions to do file access. And I want to try disk mode, directly interfacing with the disk hardware with port I/O from protected mode. And maybe one thing I want to try is I want to try to create a bootloader, so a binary image that you can burn onto a floppy disk or a CD or a flash drive and plug it in, and you can boot your computer from your handmade assembly program. And I want to try to maybe kick the CPU into long mode, which is the 64-bit mode, and play around with that. So those are some ideas of stuff I would be doing in ASM, but yeah, that's it, basically. Those are the two things that I'm thinking of doing in a live stream series. This not going to be done in one session, probably a few sessions, and this will obviously all be different sessions, I think. But what I want to know from you guys, I want to know two things. First of all, I'm probably going to be streaming, if I do this, my general streaming time will be from, in Japan time, which is not going to make sense to you guys, it's probably going to be like around 10 a.m. on the weekend. So Saturday or Sunday, 10 a.m., which for you guys is going to be Friday or Saturday, 8 p.m. if you are in the, American Midwest, basically. So evening, I want to know, just general show of hands, who would prefer Friday evening and who would prefer Saturday evening? Sunday evening is out of the question. It doesn't work. I'd have to stream 10 a.m. on a Monday, which is not, my employer would probably not be too impressed with that. So what would you prefer, Friday evening or Saturday evening? Sorry to you guys who are outside of the North Americas, because it's just not going to work. I can't think of a good time to stream to you guys as well. But that's the way the world turns. It's the realities of living on a spinning rock of molten iron that's flinging itself around the sun. Anyways, so that's one thing, when. And the other thing is, what would you guys prefer, assembly or designing a CPU? What is more interesting to you? So yeah, just leave maybe some comments on the video. Let me know what is your interest and what is your preferred time, or any other comments or suggestions on this idea about a live stream. I'll probably be doing it on YouTube streaming, not Twitch. But who knows, maybe in the future I'll switch over or whatever. It's all up in the air right now. But that's it. So a little idea for something maybe in the future. Nothing set in stone, but it's something I'd like to try. So that's that. And that's the end of the video. Like the video. Please like the video. It keeps my interest up, and it's better. It's really good for that old SEO bullshit. Driving more people to my channel, more people to the channel, makes me more motivated to make videos, makes more content for you. It's all good. It's a win-win for everyone. And yeah, any questions about anything in this video or anything else, come to the forums, say hi. Albino Papa is there, and he is a cool dude. Papa bless.